We have derived the small signal picture of a current buffer or a common gate amplifier. It's a current controlled current source of gain 1. Now we will combine it with a suitable biasing arrangement to complete the circuit. The gate of the MOS transistor is grounded. The input is connected to the source terminal. And the output is taken from the drain. And I'll for now assume that there is a load resistance connected that way. This is of course GM VGS. Okay. Now, what biasing arrangement suits this? Like before, because the source terminal is not connected to ground, we use source feedback biasing. Okay. In source feedback biasing, we connect a current source to the source terminal, and the drain, just for biasing purposes, is connected to the supply voltage VDD, and the gate is biased with a voltage divider R1 R2, which is powered from VDD. Okay. Now, to this biasing picture, we have to combine this signal picture. Okay. So first of all, the input is connected to the source, and we'll assume as usual that the signal frequency is above a certain value. It doesn't include DC, so we can couple it through a capacitor. Okay. I'll assume that it is connected like this. Okay. And then the load has to be connected between drain and ground. Here a drain is connected to VDD, which means it's connected to small signal ground or incremental ground in the incremental picture. It has to be removed from that and connected to the load. And again, if the signal is above a certain frequency, what we can do is we can have an inductance L2 whose reactance is much more than the load resistance, and we can AC couple the load resistance. Okay. This is the exact same arrangement we used with the voltage controlled current source. Okay. Now of course, if inductors are too bulky and we cannot use them, we can replace L2 with some resistor RD, and if you do that, of course only a fraction of the current can flow through RL. Okay, because you cannot make RD indefinitely large. That will mean making the supply voltage VDD very large as well, so that's not reasonable. So you will end up having to share the current between this drain bias resistor RD and the load RL. Okay, but you know how to analyze that, so I'm not going to go through that in detail. You can either use this L2, which is a large inductance. By the way, whether the inductance itself is large or not depends on the frequency as well. Okay, the reactance of this has to be much more than RL. If you go to a very high frequency, a small inductance has a high reactance. Okay, so it's quite common to see a picture like this in high frequency circuits. In low frequency circuits, the required value of inductance becomes so large that you don't use it. Okay, and many times this inductance, which is very large, it's referred to as a choke. Okay, essentially there is no current flowing through this. You can think of it as choking the current that is going into the small signal ground and letting it all go into the load resistor. Okay. And the gate has to be connected to small signal ground. Now if you look at it, it is connected to ground through R1 and R2. Okay, the actual picture looks like this. The gate terminal is connected to ground through this. Okay. Now so far we have been assuming that the gate current is 0. So if the gate current is 0, even if you have a resistance between gate and ground, this will be at 0 volts. Okay, so that seems adequate. But it turns out that, and we have not studied this part yet, there is a capacitance between gate and source. Okay, there is a capacitance referred to as CGS between gate and source. Okay, so because of that, if you connect it up just like this, that is, it is connected to ground through R1 and R2, the gate voltage will not be exactly 0 for signal frequencies. It will be at 0 voltage for DC increments, but for signal frequencies it may not be exactly at 0. So we always connect a capacitor also, a large capacitor, let me call it C3, between the gate and ground. That makes sure that the gate is connected to ground. Okay. Now we have not studied the transistor model including this capacitance, but take it from me that in a common gate amplifier you do connect a capacitor from gate to ground. And how much should this be? It should be much more than CGS of the transistor, and CGS of the transistor is of the order of Cox times WL. Okay, you are familiar with these terms Cox, W and L from the MOS model. Okay, now of course, because we have not studied these things, as far as we are concerned, we will assume that we will always connect a C3 that is very large, so this point is shorted to ground for signal frequencies. Okay, so this is now the complete common gate amplifier with biasing. You can see that the output part of it resembles what we had for the voltage control current source. That's not surprising. Voltage control current source and a current control current source, the output parts are the same, so it looks nearly the same. Okay. Now let me put the circuit down again. I'll show this as infinity, meaning it's so large that it is a short circuit. And I'll show a resistor RD instead now, and we can also have another RL here. Now we connected a current source at this point, but many times people like to operate with voltages. So even though it's a current controlled current source, we connect a voltage source in series with a resistance. Okay, so VI in series with RS. Okay, now of course you know that this part of it is equivalent to having a current source VI by RS in that direction. Keep in mind the direction for current we have been taking here is going downwards, whereas if I have VI with the upper terminal positive, it will be upwards in parallel with a resistance RS. Okay, so it behaves in exactly the same way as before, and this current here is approximately equal to VI by RS, or rather minus VI by RS, because the polarity of this is reversed. In this case, this current here I naught was approximately equal to the input current, but the input current is pointing downwards. So in this case, I naught is approximately minus VI by RS. Okay. And if you again take the output voltage instead of the output current, what will this V naught be? It will be minus I naught times RD parallel RL. Okay, this is assuming C2 is large enough for it to be a short circuit and so on. If that's the case, then the output voltage with a voltage source input will be VI times RD parallel RL by RS. Okay. So you can use it with a voltage input. Of course, in this case, you can see that the gain depends both on the load resistance and the source resistance. Okay, so just because you apply a voltage input and take a voltage output, it doesn't mean this is a voltage controlled voltage source. Okay, a good voltage controlled voltage source should also have a very low output resistance and a very high input resistance. This has exactly the opposite. The input resistance is very low and the output resistance is very high. So this is really a current controlled current source, but you can operate it with a voltage source in series with a resistance, and also consider the voltage as the output. Okay, in that case the gain will be some resistor ratio, which can also be accurately set, and it is sometimes used like this. Okay, so when you see this common gate amplifier, you do see it sometimes with a voltage input and the gain is this one. Of course, this is the approximate gain. If you use the exact value, again I have neglected RDS of the transistor. As I said, RDS is important for the output resistance. For other things it makes a small change and nothing else. Now we know that this I naught is approximately minus Vi by Rs, but it's really minus Vi by Rs times Gm by Gm plus Gs. Okay, so this number is close to 1 but not exactly 1. So the actual output voltage will be Vi times Rd parallel RL by Rs times this Gm by Gm plus Gs, and this also can be written as GmRs by GmRs plus 1. So as long as GmRs is much more than 1, it reduces to this, if GmRs is much more than 1. Okay, so that's it about the common gate amplifier. It's a current controlled current source with gain 1. It's a current buffer. So what it does is it takes a rather poor current source. This current source has a resistance Rs and it gives you the same current but with a much higher resistance. Okay, looking in here, you know that the resistance is Gm Rs Rds plus Rds plus Rs. Because of this term, the resistance looking in here is much higher than Rs, so it gives you a much better current source. And it's exactly like the voltage buffer. A voltage buffer can take a voltage source with a high series resistance and make it look like a better voltage source, the same voltage but with a much smaller output resistance. Okay, so this current buffer serves a similar purpose and it's also a very widely used building block. Okay, now as far as capacitance values are concerned, we've already calculated these things, so I'm not going to go through that. The value of C2, we have calculated it so many times. If you want C2 to be like a short circuit so that the output voltage is the same as replacing C2 by a short circuit, then the reactance of C2 must be much smaller than Rd plus RL. But if you want the drain voltage and the output voltage to be nearly the same, then the reactance of C2 must be much smaller than RL by itself. Okay, and similarly you can calculate it for C1. Reactance of C1 must be much smaller than what appears across it, which is Rs plus 1 by Gm. Okay, so I am assuming you can calculate these because we have calculated these things in other contexts. Okay, so I am not going to go through that again. So that completes the current controlled current source or the common gate amplifier. Okay, again common gate amplifier is usually presented as a basic building block. Now we like to think of it as a feedback network which forces the output current to be equal to the input current by adjusting VGS appropriately. Okay.